Okay, today we're looking at 2.5, which is our polynomials. Specifically, we're looking at complex zeros. So the first thing we're looking at is what we refer to as an imaginary unit. We simply call that I, which is equal to the square root of -1. You could think about it, though, as a quantity whose square is -1. So when you square I, right, you get -1. Or you can think about it as whenever you take the square root of some negative number, right, it's equal to the square root of that positive number times I. If you have a number in the format a plus bi, right, where they're real numbers and I is the imaginary unit, we call that a complex number. Then when you've got a minus bi and a plus bi, right, these are called complex conjugates. It's important to note here the imaginary part is the part that switches, the real part is equal. But the cool thing about it is their product is a real number. So when you multiply it together, you should get a real number. Okay, so let's just review some things about imaginary numbers. So if you have I squared, we just talked about that, we do get -1. As for higher powers of I would say there's two ways you could think about it. You could say, well, I to the 0 is 1, right? I to the first is I squared, we said, is -1. Which means I cubed, which you could almost think about as I to the first times I squared, is a -I. And then as you go to I to the fourth, it goes back to the top. So it follows that same pattern. The second way to think about it is to say, okay, I can think about it as a graphing, kind of our real and complex, real and imaginary unit. So we start with 1, and this is I to the 0. As you multiply by another I to the first is just I. As you multiply and we get I squared, we get a -1. We're back to the real numbers. As we do I to the third, we get a -I. And then you go back around. So it's the same as I to the fourth, I to the fifth, etc., right? So we keep going in this rotation, which there is actually some math behind that, about imaginary numbers being this rotation of 90 degrees, in case you're wondering. Okay, so as you look at something like this, I to the 61st, I would say, okay, well, it has a pattern of 4, so let's divide this by 4. We end up with 15.25. So you could say, well, it has a remainder of 1 then, right? 0.25, that's 1/4. So we get, this is the same as I to the first, so therefore it's just I. If I take 35 and divide it by 4, I get 8.75. So I've got a remainder of 3/4, right? So therefore, this is the same as I to the third, which we said is the same as -I. Okay. On these next ones, we want to say, okay, we got 7 minus the square root of -144. Square root of 144 is 12, and the negative part is I. Okay, on this one, we get -6, and then the square root of 64 is 8, and then the negative part, once again, is I. So this is the same as -48I. Okay, then on here we have square root of -9 is 3I, times the square root of 49, -49 is 7I. So we get 21I squared. We know I squared is the same as -1, so we get -21. Be careful. This one you may be tempted, right, to multiply what's inside the square root first, but we do need to simplify those square roots before we multiply. And maybe think about that as order of operations. We always take care of exponents first, right? And technically those square roots have an exponent of 1/2, right? So we want to take care of that before it. Maybe that's one way to think about it. Okay. Next, 2 times -7 is -14. I times I is I squared. So we get -14 times the -1. We do end up with +14. Last but not least, we've got a -6 I squared. -6 squared is 36. I squared is just I as a -1. So we get 36 times the -1. We end up with -36. In general, when you are simplifying these, you should never have a power higher than I to the first, right? Because then we do go back kind of to that rotation like we did in A, B, and C. Okay, The next part is we want to find the complex conjugate. So remember, our complex conjugate has the same real part, so of 9, but an opposite imaginary part, so plus 4i. So then, if we wanted to find the product, we're going to go ahead and multiply it. And remember, the cool thing about this is when we do multiply, we should end up with a real number. So let's see. As we distribute through, we get 81 plus 36i minus 36i minus 16i squared. So we get 81, the 36i's cancel, but we get negative 16i squared. So that's 81 minus 16 times a negative 1. So we end up with 81 plus 16. So we get a total of 97. Well, you know I'm at school today, right, guys? Okay. The next one, if we want to find real zeros, and we've got this quadratic. In general, sorry, this just says zeros. Notice it doesn't say real, so that's probably a good indication to you that it may not be real, right? They could be imaginary or complex. Notice I can't think of anything that multiplies to 5 and adds to negative 2. So you can't factor it, so we're going to use our quadratic formula. So x equals negative b, which in this case is a negative 2, so a negative of a negative 2 is positive 2, plus or minus the square root of negative 2 squared, minus 4 times a is 1, times c is 5, all divided by 2 times a is 1. So we get 2 plus or minus negative 2 squared is 4. 4 times 1 times 5 is 20, so we get 4 minus 20, right? All over 2, so we get 2 plus or minus the square root of negative 16 over 2. So we've got 2 plus or minus the square root of negative 16 is 4i, all over 2. Both the parts in the numerator are divisible by 2, so we get 2 divided by 2 is 1. 4i divided by 2 is 2i. So our two zeros here are 1 plus 2i and 1 minus 2i, which makes sense because it is a second-degree polynomial, right? And so there should be 2 solutions, which is what the fundamental theorem of algebra says. Remember, it says, hey, whatever degree it has, it should have exactly that many zeros, including multiplicities, and I'm going to add in there including complex numbers, right? The new one about the pairs here is that actually, right, if you have some as long as your polynomial has real coefficients, if a plus bi is a 0, then the complex conjugate is also a 0 of that polynomial. So notice they do come in pairs. So let's go ahead and go through. We said find all the zeros of the polynomial and completely factor it to linear and irreducible quadratic factors. So something like this, we could definitely talk about what we did last time, right? Our p divided by q. So our p is the factors of 12 over q is going to be the factors of 1. So here we just basically have the factors of 12. So like 1 and 12, we've got 2 and 6, we've got 3, I ran out of room, sorry, and we got 4. Okay, that was a little messy. So with those factors, you could say, okay, well, we got to start plugging things in. Remember, in general, I don't want to waste a ton of time on the test, so I would likely tell you like the first one to kind of get you started. Either that or if it's multiple choice, you kind of can look back at the answer and kind of figure out some of them. So here, I'm going to tell you, let's plug in negative 3. So going back to our synthetic division like we did last class, we're going to write the coefficients of that polynomial. We bring down the 1. We're doing 1 times negative 3 is a negative 3. We add the column, we get 0. 0 times negative 3 is 0. We add the column, we get 4. 4 times negative 3 is negative 12. We end up with 0. That is a good sign. It means that negative 3 is actually a 0. Which leaves us with the polynomial x squared plus 4 equals 0. Okay, you could write a 0x in the middle there, and I just don't think it's worth it. So if I wanted to write it as some factors, this is the same as when you have a solution of x equals negative 3, right? If x equals negative 3, that means that x plus 3 equals 0 is a factor. So x plus 3 would be in our equation, and the other part is the x squared plus 4. x squared plus 4 isn't a reducible quadratic factor, meaning it can't be factored, right? So when we say linear ones, we mean like degree ones. So like x plus 3 is a linear factor. Okay, so now we got to find our zeros. There should be 3. We already know negative 3 is one of them, but we got to figure out what the other 2 are. So if we've got the equation x squared plus 4 equals 0, this one is not factorable. You could use a quadratic formula, but if you just got a square and move that 4 to the other side, and then think about taking the square root, you'll save yourself a lot of time. So when we take the square root, we do get 2 answers, plus or minus, and the square root of negative 4 is 2i. So x equals positive 2i and x equals negative 2i. So here is the answers they're looking for. I'm going to do one more thing. If I wanted to rewrite it with the imaginary factors, I would have x plus 3, right? That was the solution, x equals negative 3. For x equals positive 2i, you'd have x minus 2i. And then for negative 2i, x plus 2i. That is another way to write your polynomial. Okay. Same thing here. I could go through, I could find it, but more likely I'd tell you like, hey, x equals 1, multiplicity 2. Then you're down to a quadratic, and you totally should know what's going on, right? So here, let's go ahead, let's plug in 1, let's write our coefficients. Gonna perform some synthetic division. So 2 times 1 is 2, we get a negative 5. Negative 5 times 1 is negative 5, we add the column, we get 9. 9 times 1 is 9, we add the column, we get negative 6. Negative 6 times 1 is negative 6. We add the column, we get 0. Good sign. Same thing again. Since it's multiplicity 2, it happens twice. So do your synthetic division. We get a remainder of 0 again. Good sign. So once again, we're saying, okay, the polynomial we're left with is f of x equals x minus 1, and technically that's x minus 1 times x minus 1, so I'm going to write it as x minus 1 squared, and we're left with this quadratic 2x squared minus 3x plus 6. And you could say to yourself, well, does anything multiply to 12 and add to negative 3? And from, like, whether you think about it for a little while or what, but that's not factorable, right? There's nothing that multiplies to 12 and adds to negative 3. So therefore, we're going to look at the quadratic formula. X equals our negative b, so 3 plus or minus the square root of b squared, negative 3 squared, minus 4. A is 2, c is 6. All divided by 2 times a is 2. So we'd get 3 plus or minus the square root. We do get 9 minus, what do we have there? 24/48. Yeah, okay, let me just delete some of that. All over 4. So we get 3 plus or minus the square root of negative 39, all over 4. And the only other thing that I would say in this case is you should take the negative under the square root. So we'd have 3 plus or minus I square root of 39 over 4. The square root of 39 does not simplify anymore. So here our zeros are 1, right? That does have a multiplicity of 2. 3 plus I square root of 39 over 4. And 3 minus I square root of 39 over 4. And this is the answer they were looking for. However, I'm going to take it one more step. If I wanted to write it in fully linear factors, I would leave the x minus 1 squared. And for these answers, you could write it as x minus the 3, right, plus I square root of 39 over 4. And the x, and if I guess x plus 3 minus I square root of 39 over 4. If you wanted to get fancy, you can maybe multiply that 4 through, but then just make sure you have that 3 plus the I square root of 39 in parentheses. Okay. So now we're going to go ahead and create some polynomials. Create a polynomial p which has the desired characteristics. You may leave the polynomial in factored form. So it says, hey, we've got some zeros. So we've got the zeros of p are plus or minus 2 and plus or minus I. So let's just write that. What does that look like? So positive 2 means x minus 2. Negative 2 is x plus 2. If you got positive I, same thing, x minus I, right? And a negative I, you're subtracting a negative, so it's x plus I. Here it says the leading term is 42x to the fourth. It makes sense. There's 4 solutions, so it should be a fourth degree. And then the way that I make it have a 42 up front is I add that 42 in for a. And we've got our polynomial. Okay. On this next one, it says a polynomial degree 3. It has real coefficients and 0 at x equals negative 7. If it's helpful for you, I'd maybe write that, like move it to the other side, so x plus 7 equals 0. So remember that x plus 7 is going to be what's in our polynomial. So p of x, we don't know it in here. They didn't give us the leading term, but we're going to have x plus 7. And then the thing here is when you have this, x equals negative 3 plus 3i, I would maybe go through and just add it to the other side. So we'd have x plus 3 minus 3i. Or you could think of it as x minus, and then that part in parentheses. But people sometimes forget the parentheses. So I would just move it over to the other side and set it equal to 0. Okay. The issue we now have is, hey, that's only 2 zeros. So where does the third 0 come from? Remember, our complex conjugates come in pairs. So if we have x equals negative 3 plus 3i, we also have negative 3 minus 3i, which means that x, if I move it to the other side, plus 3 plus 3i is also a 0. Okay, so we're going to go ahead. We have now 1 point here. So they're telling us that 252 is the y-intercept, so I'm going to plug in 0 for x. So I get 7, I get 3 minus 3i, I get 3 plus 3i. And to make your life a little easier, we know that complex conjugates should give us a real number. So like whether you want to do it on the side or multiply it over there, let's see just with the complex part. So the 3 minus 3i and the 3 plus 3i give us. So we get 9, we get a negative 9i, we get positive 9i, we get negative 9i squared. Notice the 9i's cancel. The negative 9 and the I squared is a negative 1. So we really get positive 9. So really here we just have 9 plus 9. So we get 252 equals a times 7, and then 9 plus 9 is 18. So we get 252 equals a, and then 7 times 18 is 126. So as you divide both sides by 126, a equals 2. So our polynomial here, as we rewrite it, you can leave it in factored form, is 2 times x plus 7, and then x plus 3 minus 3i, and then x plus 3 plus 3i. Okay. We've got kind of 2 more to look at here. So these ones, it does say expand it, so we cannot leave it in factored form like we did kind of for those first 2. So we are going to create a degree 3 polynomial having zeros of 5 and 1 and a leading coefficient of 1. So p of x equals, we can put a 1 out front. I'll do it just there so we know we had an a. We didn't have to solve for it. A 0 of 5 means x minus 5. A 0 of 2i is x minus 2i. Notice, though, we're not to degree 3 yet. So you got to remember, hey, if you got positive 2i, I also have negative 2i. So that's x plus 2i as a factor. Okay. I highly suggest in all these examples that you start by taking care of the imaginary part because it comes a lot nicer when you multiply it out. So as I multiply this out, I would have x minus 5. Actually, I'm going to do it in a little box. I think that helps you just stay organized. It's not to say you have to do a box and you can't distribute, but x plus 2i, x minus 2i. We get x squared. We get 2ix. We get negative 2ix. Notice they're canceling. We get negative 4i squared. We know I squared is a negative 1, so this is really just 4 in that box. So we now have x minus 5, and then x squared plus 4. See how nice and easy you made life, right? So now let's distribute through. So p of x equals x cubed plus 4x minus 5x squared minus 20. And I am going to write it in descending order. It's not to say that you have to, but I think it just makes it look a little bit nicer as a polynomial. And we've got our polynomial that has the zeros indicated. Okay. We've got the next one. We've got it touches but does not cross at 2 0. So notice here that means that, hey, it's got to be an even multiplicity. And it doesn't specify what. I would make your life easy, maybe just say, like, let's say 2. Okay, then we have x equals 3 plus I. I would move that to the side, so remember that's going to be the factor x minus 1 plus 3i equals 0. And remember, hey, there's another pair that comes with it. X equals 1 plus 3i, right? The imaginary part changes. So that's the same as x minus 1 minus 3i. If you picked up on patterns, just like we did kind of before, notice the only thing that changes here is that imaginary part. Okay. Next, let's go ahead and it says a little bit, it has the following end behavior. So, hey, on the right side of it, it goes down, and on the left side of it, it goes up. And here we do have a degree. Oh, no, sorry, I read that wrong. And then the left side, it goes down as well. So we do know that there's a negative coefficient. It doesn't specify what that negative coefficient has to be, so there's lots of options, right? Lots of answers, possibly answers, I'm going to say. So we're just talking about one of them that fits this condition, but there are others. So if I call it p of x and I want a negative coefficient, I think an easy negative coefficient is negative 1. Okay, x equals 2 has an even multiplicity, so x minus 2, I'm going to call that squared. Okay, over here we have x minus 1 plus 3i, x minus 1 minus 3i. Okay, now we just got to multiply. I'm going to leave the negative 1 out front till the end. I'm going to multiply x plus 2 times x plus 2. I'll do that over here. X minus 2 times x minus 2. We get x minus 2, x squared minus 2x plus 4. So this is the same as x squared minus 4x plus 4. I'm going to do, once again, a box here for this complex roots. So x minus 1 plus 3i, x minus 1 minus 3i. X squared, we get a minus x, we get plus 3ix. We get a minus x, we get a 1, we get minus 3i. We get minus 3ix, we get plus 3i, and we get negative 9i squared. Notice the terms that just have I, they cancel out. That makes life pretty easy for us. This negative 9 times I squared is just negative 9 times negative 1, so it's a positive 9. So we're going to have our x squared. We've got minus 2x, and then we've got a 1 plus a 9, so we got plus 10. Hey, that's not too bad. I could probably distribute now, right? I got a negative 1. And now as we multiply through, we get x to the 4th minus 2x to the 3rd plus 10x squared minus 4x to the third plus 8x squared minus 40x. Last but not least, multiply the 4 out, we get plus 4x squared minus 8x plus 40. Okay, let's see what combines, because I think there's a bit that combines. We get x to the fourth. With our cubes, we have minus 6x cubed. Then we have plus 22x squared minus 48x plus 40. Last but not least, we got to change all the signs. So we get negative x to the fourth plus 6x cubed minus 22x squared plus 48x minus 40. And we are done. Well, B is probably harder than what you normally see, and A is probably a little bit easier. I will say they like this concept a lot, so it quite often appears on midterms and finals as a heads up. Good luck with the